Hey everybody, Dr. A here, and in this video we're going to be exploring another example of transverse shear stress. So let's go ahead and get started. In the given information, we're being told that for the beam section shown here, it is subject to 3 kips of shear force, and we're being asked to compute the shear stress at a point just above and just below the flange web interface. So the point that's just above that interface is point A. We see that right here. We see that top little red dot just above this interface, which means it's barely into the flange. You can think of this as like one little pixel into the flange, okay? And then the point just below the flange web interface is point B, the second or lower red dot, which is just barely into the web, 1 pixel into the web. So the cross-section shape is a T shape. The width of the flange is 10 inches. The width or thickness of the web is 2 inches. The height of just the web itself is 7 inches, and the vertical dimension or the height of the flange is 2 inches. So let's go ahead and get started. So the first thing we can do is write our governing equation. Tau is VQ over IT. Now, the first thing to recognize is that we're given V. We know what that shear force is. That's the 3 kips that were given in the problem statement, okay? Now, do we know the thicknesses? Well, pretty much. So thickness T is going to depend on where in the cross-section we are. So when we are calculating the shear stress for point A right here, we're going to be barely into the flange, which means the thickness we're going to use is 10 inches. When we're interested in looking at point B, we're going to be barely into the web, and for that point, we're going to use a thickness of 2 inches. So I'm going to make a note here. I'm going to say the thickness when we're looking for the stress at point A is going to be 10 inches, and the thickness when we're looking at the stress at point B is going to be 2 inches. So I'm going to use each of those values to calculate my 2 shear stresses that I'm looking for. Now, the real work that we're going to have to explore is how do we calculate Q and how do we calculate I, all right? In either case, we're going to first need to get the location of the centroid Y bar, okay? So I'm going to use my original figure to help me out here. I'm going to call this bottom surface the datum, okay? This bottom thing down here is going to be the datum. And so that's going to allow me to go ahead and calculate Y bar as the sum of Y sub I, A sub I, divided by the sum of A sub I. And of course, we go from I equals 1 to N. And in this case, there's 2 pieces here. So I'm going to just go ahead and, treat this as 2 rectangles. We have the flange, and then we have the web rectangle, okay? And so going 1 piece at a time, if I start with the web, I can say 7 inches times 2 inches multiplied by 3.5 inches plus 2 inches times 10 inches times 8 inches, all divided by the total area, which again is 7 inches by 2 inches plus 2 inches by 10 inches. Now, this is just a simple centroid calculation. I get Y bar is 6.147. If you're rusty on your centroid calcs, you need to go back and review that. I've got a video in my statics playlist that can help you refresh your memory on that. But this is not statics anymore, so I'm not going to go into any more detail with that. So Y bar is going to be about right here. And that is that value of 6.147 inches. That's the centroid of the entire shape, okay? So that means that, right here is our neutral axis, all right? Now, the next thing I'm going to go ahead and do is calculate the moment of inertia about that neutral axis, INA, all right? And so again, this is also a static step. I'll show my work, but I'm not gonna delve into all the details here. That's gonna be the summation as I goes from 1 to n of I sub x sub I plus a sub I d sub y sub I squared. Again, if you're a little rusty on this, look at my statics playlist to help you refresh your memory on how to calculate centroid of a composite shape. So here we're going to have two rectangles. So we have a BH cubed over 12 for the web piece plus an AD squared. The area of the web is 14 square inches times 6 minus 147 inches minus 3.5 inches, and don't forget to square that, plus, and we have a term for the flange. There's a BH cubed over 12 term for the flange, plus an AD squared term for the flange, so that's 20 inches squared times 8 inches minus 6.147 inches squared. Again, if you're rusty on moment of inertia calcs, that's a statics topic. Take a look at my video in the statics playlist on moment of inertia. We punch this through and we should get 230.6 inches to the fourth. If I were you, I would maybe pause the video, punch this through, make sure you are able to see and figure out where all this comes from, okay? Again, at this point, we're not even doing mech of materials yet. This is really just some simple static steps, okay? The next, so we can go ahead and check off our moment of inertia value, I, okay? Now, the last thing we need is really Q, okay? So here's where I'll show a little bit more work because this is, kind of a point of confusion a lot of times. So we're going to say compute Q, all right? And so I'm going to go ahead and redraw my section here. All right, and we know that's 2 inches, 2 inches, 7 inches, 10 inches, okay? And I'm gonna put my little interface here. Now, remember, we can write Q as Q equals A prime Y prime bar, all right? Now, A prime is the area above or below what we are interested in, the plane that we're interested in. So if we're interested in what's going on around this interface, A prime could either be the flange or the web. Either one is fine, okay? So I'm going to say, let's call the flange A prime, all right? And so if that's the case, A prime is going to be 20 square inches, all right? Now, what about Y prime bar? Well, Y prime bar is the perpendicular distance from the centroid of A prime to the overall centroid of the entire section, okay? So that overall centroid, we calculated that earlier, that's Y bar, and that was the 6.147 inches, okay? And so what we're looking for is this distance here, Y prime bar, okay? And so Y prime bar is going to just be 8 inches minus 6.147 inches. Now, why is that? Well, again, your 8 inches is the distance from the point of the centroid of A prime all the way down to the bottom. That's this distance right here. That is 8 inches, okay? And then you say that distance, 8 inches, minus regular Y bar. And what does that leave you with? That leaves you the distance in between those 2 points, okay? And so we can punch that through, and we get 8 minus 6.147 is 1.853 3 inches. And so we can get our Q value as 37.06 inches cubed, okay? And so now we have Q, all right? So now what we need to do is compute tau 2 times, one for point A and one for point B. So we're looking for the shear stress, again, right above that interface, and then a separate value for the shear stress right below that interface, okay? So let's write that out. We're gonna say tau A is VQ over I about the neutral axis, T sub A. And so we say 3 kips times 37.06 inches cubed divided by 230.6 inches to the fourth times 10 inches. And so we punch this through and we get 0.0482 KSI, or we could rewrite that as 48.2 PSI. So that is one of those shear stress values. We can also get tau B as VQ over I about the neutral axis times T sub B. And so we get 3 kips times 37.06 inches cubed divided by same moment of inertia, 230.6 inches to the fourth, but times a 2-inch thickness because we're in the web here. And we punch this through and we get 0.241 KSI. And so we could write this as tau B as 241 PSI. And so these become our two values, tau sub A and tau sub B. Okay, so if you found this video helpful, please hit like and subscribe and be on the lookout for other content similar to this. Thanks for watching.